In this lesson, we are going to fix the issues we currently have with our window instance is on the buildings. To begin, we are going to take the separate elements, node and the instance on points, node, and place them into a new node group. As we have done previously, we will rename the sockets of the group to make it more readable. The output socket will be called building instances, and the input will be renamed to building proxies. We will also expose the seed values from inside the group so they are available from the outside. Let us rename the group to building instances to keep things clear. Then, inside the group input, we will bring in building set seed and window seed so that they can be controlled directly from the modifier panel. Now, let us go back inside the node group. Earlier in the course, when we created the system for generating floors, we mentioned that we would want to wrap each building instance inside A for each element. Setup. This way, we can handle the instance is one building at a time. So now we will add A for each element, node, and set its type to instance. We will make sure the geometry input is connected to the proxies, and that the output is fed into the loop correctly. Finally, I will add a reroute node at the output so that we can view just one instance at a time, which will help when previewing. The first thing we need to fix is that, currently, all the windows are being generated on the points, that is, on the vertices of the mesh rather than on the faces. To solve this, we first need to realize the instances that are coming into the loop, so we have access to actual mesh data instead of instances. Next, we are going to use a mesh to points, a node. This node works similarly to the curve to points node that we used earlier in the course. It lets us define where the points should be generated. By default, its place is points on the vertices, but we can change this to edges, faces, or corners. In our case, we want to use the faces, so we switch the setting to faces. Now the windows are being generated in a way that looks much more grounded and natural. If I move the viewer to compare the previous setup, you can see how it looked before, and now how it appears with the updated point placement. Now we need to take care of orientation. Right now, all of the instances are facing forward, which clearly is not what we want. To fix this, we will store a named attribute after realizing the geometry. We will do this on the face domain, and we will store the normal direction of each face. This will allow us to use the actual face normals for orientation. We will name this attribute face normal. We could just use a capture attribute node to grab the face normals directly. But once this setup is complete, we are going to duplicate all of these nodes not just for windows, but also for doors and commercial buildings. If we use a capture attribute approach, it would result in lots of connections and reroutes stretching across the node tree, making everything messy. So instead, it will be easier to simply store the normal as a named attribute, which we can access wherever we need it. Let us now bring in a named attribute node. We will reference the one we just stored, face normal. If we try plugging this directly into the rotation input of our instance, the result is going to look incorrect. The instances will be rotated in strange directions. Clearly, this is not what we want. That is because the rotation input expects a vector to be converted into a rotation, and the data type of our face normal, a blue vector, needs to be adapted to the pink rotation input socket. To convert it properly, we are going to use the align Euler to vector node. We connect our normal vector into the input and the output rotation into the rotation input of the instance. At first, this still looks off, and that is because we are aligning the z-axis by default. But in this case, we want the y-axis to align with the face normal instead. Once we switch the axis from z to y, the result looks much more correct. Next, we need to deal with the scaling of our instances. If we switch to the top view and look closely, we can clearly see that the instance in the corner does not fit properly. But when we examine the mesh, we see that it contains a single clean edge or a full row of faces. In theory, the width of that should be exactly 3 meters based on how we set up our resampled curves. However, it is clearly not lining up. We know that our window assets are 3 meters wide, but here the spacing is off. This mismatch happens because the resample curve node we used earlier is not 100% precise. As a result, the actual edge lengths vary slightly across the model. To fix this, we need a way to properly scale each instance only along the x-axis. We will do this using another stored, named attribute. Let us add a store named attribute node and set the domain to face. We will call the attribute xScale, and its data type will be float. To calculate this value, we need to look at the mesh and get the face areas. we can enable wireframe view and then use the face area node to compute the area for each face. The area should correspond to the width multiplied by the height. Since we know that all our faces are 3 meters tall, the width must be the area divided by 3. Or more precisely, since height times width is area, and height is 3, we can divide the area by 9 to extract the x scale. Let us plug the result of that scale calculation into the named attribute. We can tidy up the layout a bit so everything is clearer. Now let us disable wireframe view and look at the final instances again. We are going to take another named attribute, node, and reference the scale we just stored in this case, x scale. Then we will add a combine x, y, z node. We connect the x scale attribute to the x input. The y and z values will remain set to 1 because we only want to affect the width of the instances, not their height or depth. Now, if we plug this combined vector into the scale input of our instance, the windows should properly fit each face. When we look closely at the building edges now, everything aligns exactly as it should. This solves the fitting issue. Earlier, we said we would also plug the index of each building into the group ID input of our separate elements node. That way, each building can receive its own individual window style. Since we are working inside a for each element loop, we can just use an index node here. Let us connect the output of the index directly to the group ID input. Now each building gets a different window set. If we adjust the set seed, the window styles will change. And if we adjust the element seed, we get different window variations per face. Everything is looking good. There is still one more issue. Although it might not be immediately obvious. As I look around the scene, I can find a building that clearly shows the problem. Here it is. We can see that the windows are being generated on the wrong side. They are appearing inside the building rather than on the outside. This is why we are seeing incorrect geometry and misaligned instances. Let us go back to our building proxies and turn on face orientation in the viewport. Now it is clear that some of the proxies have their face normals flipped inwards. That is what is causing the windows to face the wrong direction. Normally, there is a way to recalculate normals for mesh geometry directly inside geometry nodes. But in this case, it will not help us because these buildings were created using curves. So instead, I will step out of the node group and go back to the part where we generated the building curves. If I place a unify curve tangents node before the extrusion, that will make sure all the curves have consistent direction. This ensures that when we extrude the floors, all the normals of our proxies will be facing outward. Now that we have done that, let us turn off face orientation and check the result. Everything is aligned properly again. As soon as I place this here, the alignment of all our buildings is instantly corrected. Let us turn off face orientation now. In the next lesson, we will take these building instances and use them to separate elements for our doors, as well as for our commercial buildings,